Hello, everyone. So this is the last part for the simple linear regression. Okay, now we will talk about transformations and the diagnostic plots of the residuals. Okay. So first, let's concentrate a bit on what do we mean by a linear model. Okay. So for a linear model, we mean the linearity in the parameters. Okay. So beta 0 is a parameter, beta 1 is a parameter. So this is a linear model, right? Well, this is ln yi plus beta 0 plus beta 1 times ln of xi plus epsilon I. Is it linear? Well, although you may think that yi, you just take the natural logarithm of y and natural logarithm of x. So this is not linear. Well, it's not the case. What you can do is just instead of ln of y, just call this as, let's say, I don't know, yi prime, okay? Any variable. It's equal to beta 0 plus beta 1 times xi again, prime, or let's say yi star, okay? Xi star plus epsilon I. Then you have two variables, yi star and xi star, and the rest is the same, right? So you have a linear model depending on y and xi bar. So what we mean linearity is in terms of parameters, okay, not in terms of the variables. So, well, this model, let's just look at this one. Well, yi equal to beta 0 plus beta 1 times xi to the power beta 2. Well, this is not linear. Why? Because you have a parameter here, and this parameter is not linear in terms of the equations. So what we can do is we may just use some functional transformations, right, to make a nonlinear model linear, or to ensure that the model assumptions are valid. Okay, so for example, if you think that y and x are related through an exponential function just like this, that is, if y turns out to be equal to beta 0 times e to the power beta 1 times x, what you can do is just take the ln of y, okay, and then make a regression, not y against x, but now y star against x, right? If you think that the function y and x are related to each other through a power function, which is like this, so that is, if you think that y is equal to beta 0 times x to the power beta 1, okay, then just make this transformation, that is y star equal to logarithm of y, x star is equal to logarithm of x, and then make a regression y star and make a regression on y star and x star. Okay? So if you think that, well, the relationship is reciprocal such that y is equal to beta 0 plus beta 1 times 1 over x, then simply just make x star is equal to 1 over x, right? If it is hyperbolic, then just make this transformations and then make the corresponding regressions, right? So, well, how to decide the right form of transformation? How can you say that, well, y and x are related to each other through this function or this function and so on and so forth? Well, what you can do is, of course, first make a plot y versus x. So in fact, this is what we call a scatter plot, okay, scatter plot. So what you do is simply just on a x and y axis, just plot the variables, okay? And just try to see what is the relationship between them. Okay? So for example, if you have an exponential function, let's look at the exponential function. Y is equal to, let me just write it, y is equal to beta 0 times e to the power of beta 1 times x. So if beta 1 is positive, then it turns out that, well, x increases, y increases exponentially, right? So just look at here, if x is equal to 0, e to the power 0, that's equal to 1. So here, that's equal to beta 0, right? So the intercept is beta 0. If beta 1 is negative, then as x increases, y decreases with x, but this is somehow let's say, convex decrease. Okay, so if x goes to plus infinity, then y goes to 0, right? So if you have a power function, let's look at the power function. Y is equal to beta 0 times x to the power beta 1. So now if x is equal to 0, then 0 to the power b1, that's 0. So it starts at 0, right? So if beta 1 is greater than 1, then you have something like this. It's very similar to the exponential function, but it starts at 0, right? If beta 1 is between 0 and 1, it still increases with y, but now the increase is concave. So this is a convex increase, and this is a concave increase. If beta 1 is negative, it means that then x decreases with y. So if you have an exponential function, what is that? Sorry, reciprocal function, which is if y is equal to beta 0 plus beta 1 times 1 over x, okay? So if beta 0 is positive, so if x increases, then y decreases. So what is the difference between this and the power function? So it turns out that if x is equal to infinity, then this vanishes, right? This part vanishes. Then the asymptote is beta 0, okay? So here the asymptote is what? It just goes to 0, okay? So this thing just goes to 0 there, right? And here again, if beta 1 is negative, then as x goes to infinity, the asymptote is now beta 1. So it just goes to beta 1. But here, as you see, it just goes to infinity, right? And similarly, if you have an hyperbolic function, right? Let's look at the hyperbolic function. So it's equal to y, that's equal to x divided by beta 0 plus beta 1x, right? Is it? X, yes, beta 1x. So x as goes to infinity, then the asymptote is the converging value is 1 over beta 1. So one of the very famous transformation is just taking the logarithm of y or logarithm of x. Okay, just take the logarithm of y or logarithm of x. So this is one of the the most used transformations in regression. Okay? So, well, you should be careful about 2 points. The first, well, there is an error term, okay? So you should just end up with an additive error term because the assumption of the linear regression is you have an additive error term. And the second one is, well, if you're just making a transformation if you're not making a transformation on y values, then there is no problem using the s square or r square, okay? But if you're transforming the y values, for example, if you're just taking the logarithm of y, then just be careful with the r square or s square values, okay? Because you should just calculate the r square and s square depending on not transformed y, not transformed y's, okay, not transformed y, or not y star. You should just calculate the r square and s square based on the real values of y, okay, the untransformed values of y. Okay, so we have a small example here. So, well, the pressure P of a gas corresponding to volume V is recorded as follows, okay? Well, the ideal gas law has the functional form. So it says the pressure times the volume to the power a constant gamma is equal to another constant C, right? So, well, there is a physical relationship between the variables P and V, and our aim is to find the gamma and C. So, well, first we use an error term in the model. So this is a multiplicative error term. Let's multiply it with the error term epsilon I here, okay? Then take the natural logarithm of both sides. So just take logarithm of P, okay, and logarithm of Ci here. So it turns out that this is ln of Pi. So what I mean by logarithm is just take the logarithm in base of E, okay, logarithm E, which is equal to ln. So ln of Pi is equal to what? Ln of Ci minus gamma times ln of vi plus the epsilon I star, right? And this is equal to beta 0. So what is beta 0 here? Beta 0 is ln Ci, and beta 1 times xi. So what is xi? Xi is ln Vi, right? And what is beta 1? Beta 1 is minus gamma, which is beta 1 here. And what is epsilon I star? This is my new error term, epsilon I. Okay? So this is, sorry, this is epsilon I star. This is still star. Okay. So if you just run the regression analysis, the model parameters can be estimated as, so LNC turns out to be 40.7589. So this is LNC, right? So the real value is e to the power 147589, which is equal to 2,568,000 and so on and so forth, right? And the gamma value turns out to minus 2.6534 and blah, blah. So the fitted regression line is, so ln of pi is equal to 14.7589 plus 2.6534 times ln of vi plus the error term. Or pi, right, the original one, is equal to ci times, so what is ci? Ci is e to the power 14.7589, right? So this is a large number, times vi to the power 26534 times epsilon I, okay? So, well, so these are the real points, and this line is the, it's not the regression line over ln p and ln vi, but it's the line over what? It's the line over pi and ci. So in fact, this blue line just is the line defining this relationship. Right. So, well, the next thing is that the diagnostic plots, the diagnostic plot of the residuals, right? So we said that, well, the graphical methods are useful to illustrate and detect the violation of model assumptions. Okay, so remember what were the assumptions? First of all, we said that, well, there is a linear relationship between x and y. And then we said that, well, epsilon and I are independent, they are normally distributed, they have mean 0, and then they have a constant or homogeneous variance sigma square. But of course, we cannot observe epsilon i's, but we can calculate or observe the residuals EI. Well, the residuals can be seen as estimates of the error terms epsilon i's, and what we expect is they should just imitate or mimic the behavior of the error terms epsilon i's. Okay. So since they behave like the random error terms, so their plot, okay, so the plot of the residuals, well, they should just reflect the goodness of the model. So in other words, they should just reflect the validity of the 4 model assumptions, okay? So an ideal plot of residuals versus the predicted values, okay? So that is y hat, yi hat, right? Yi hat should be something like this. So if you just plot the residuals, well, first its mean should be equal to 0, okay, just like this. Well, they should not scatter around 0 too much at the beginning or at the end, right? They should not, their value should not depend on y hat, right? And their value should not depend on each other as well. So when you just look at here, well, it turns out that they are randomly scattered around 0. Okay, so this is a good fit. This is an ideal residual plot. So what is a non-ideal residual plot, or when do we have a problem? We have a problem, okay, if you have something like this. So what is this? this is a non-homogeneous error variance, okay? So if you just look at here, the variance that is the scatter around the mean is small here, but the scatter around the mean is large in the second part, okay? So as y hat increases, the variance increases as well. So there's a problem with the assumptions here. So let's make a case study, okay? So in the manufacture of commercial wood products, it's important to estimate the relationship between the density of a wood product and its stiffness. So our aim is to estimate the relationship between the density of a wood product and its stiffness. Okay. So what we do is we just take 30 many particle boards, and we just measure their stiffness, and this is our data, right? So this is X, the density of the data, the boards, the woods, and this is the stiffness of them, right? So there are 30 many data here, right? So 15, I don't know, 15 here, 2, 4, 8, 10. 34, is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. This is 15, and I have 30 many data, okay? So if you just look at here, so this is the regression line that we fit to the model, okay? So when you just look at the regression line, well, it's not too bad, but so as you see, there are some let's say some data which is far away from the line at that extreme, okay? So in fact, maybe something like this. If you have something like this, okay, then this relationship may define this line, this curve may define the relationship between the stiffness and density may be better than a linear relationship. We don't know. We will just look and see. Okay, so if you just fit this data, it turns out that, well, this is my beta 0, this is my beta 1, and this is my R squared, right? 0.80, okay, 80%. So what does this mean? It means that your model is able to explain the variability in the data, is able to explain 80% of the variability in the data, okay? Okay. So as we said, R squared is not bad, but there are 2 points very far away from the regression line. So if we just plot the residuals, well, as you see, it turns out that, well, so here, right here, the variance is small, and here you have a larger variance, right? So it turns out that, well, the model assumptions are violated, okay? So there are clusters of positive and negative values. What does it mean? So you have positive values here, right? And there are some negative and some positive values here. And here there are again some positive and negative values here. So, well, this suggests that maybe a nonlinear or curvilinear model may be better. Okay. So the next step, we will also check the normal probability plot. So what's a normal probability plot? Okay. So, okay, so the plot of the residuals says that, well, there's a problem with the residuals, okay? There's a problem with the constant variance. So what we do next is the plot of the QQ plot, or the normal probability plot of the residuals. So what is this plot? This is also called the QQ plot, right? So how do we plot this? So generally what we do is we just order the residuals, okay? And then, for example, if we have 30 residuals, okay, then just order them, the first residue, the smallest one, then the second smallest, and so on and so forth, and the 30th one. And then just find a corresponding value for it in the standard normal random variable. Okay, standard normal random variable. How? So what we do is just order them from 1 to 30, right? And say that, okay, this is the first one. So, okay, let me just say it like this. So let me just give an example, not with 30, but with 9. So it would be much more better. Okay, let me just change this to pen. So let's say I have 9 residuals. Okay, so what I do is I just say, so well, so okay, just order the 9 residuals and assume that they are normally distributed. Okay, so the residuals are normally distributed. Then what I do is I just put assume that they are normally distributed. I just order them from 1 to 9, just like this. Okay, and so this is the first one, this is the second one, third one, and so on and so forth. So 9 residuals that just divide this region into 10 parts. Okay, so I said that, well, the area to the left of this is, so this is 10%. So the area here is, this is another 10%. The area here is another 10%, and so on and so forth. Then what I do is I just find the corresponding z value. So I just find z sub 090. Here I find z sub 080. Here I find z sub 0.70, and so on and so forth. Okay. So here, so since there are 9 many residues here, I just find z sub 090. For the second one, find z sub 080, and at last I just find z sub 010. Okay, and then plot them here. So for example, since we have how many residues, 30 many residues, you have z sub what, 100, what is this? This is 1 minus 100 divided by 31. Okay, so how about the second? This is z sub 1 minus 2 times 100 divided by 31. And at last I have z minus z sub 1 minus 30 times 100 many 31. Okay, so what you expect to see is, well, by the way, so there is a very good explanation of this QQ plot in this link. Okay, you can just go there. You also have a good explanation in your book. You can just check it. Well, I don't expect you to just draw the QQ plot by your hands. It will be given through the softwares, but it's good to know how it is plotted, right? So this is the QQ plot. What you expect to see is, so you expect to see a straight line, okay? But if you just look at here, right? So you don't have a straight line here, okay? So you have a data there, data there, okay? So let me just erase. Okay, so it's not a straight line. Okay, so if you just make it like this, you have something there. So, well, you have this up there and this up down there. So there is not a good straight line here, which says that, well, there is a violation of the normality assumption. Okay. So what we do is we just use a logarithmic transformation, okay? So what I do is just take the logarithm of y, okay? And then make the linear regression using the logarithm of y, okay? So then the regression becomes, so this is y star. So y star is equal to 8.27257 plus 0.125 times x. And it turns out that, well, r squared is 0.90. But remember, so use untransformed y, right? Use untransformed y, right? You will solve the question in the recitation, in fact, the same question with Doruk, okay? So let's look at the plot of the residuals. Just look at here, right? So the plot of the residuals are much more better. It seems that, well, they are scattered randomly around 0. Okay, that's a very good thing. And let's look at the QQ plot. So the QQ plot is, of course, it's not a straight line, a perfect straight line, but when you just look at this, it's much more better than the previous line, okay? So, well, so this confirms that the log transform model is just much more appropriate for this data, okay? So this was the previous one, okay? Just compare it with this one. So this is the transformed model. This is the original model. So if you just compare both of them, you see that, well, the original model is not good as the transformed model.